Hi everyone, so welcome back. So hopefully you've had a chance to type in that code and to have a play around with it. So I've got the code up here, so I'm just going to run that now. And we can see that SpaCy's very quick at being able to pull out um, the named entities, and just scrolling through seems to do a pretty good job. So let's just look at the first few examples. It's picked out Washington as being a geopolitical entity, FBI as being an organisation, Trump as being a person, Hillary Clinton as a person, Russia a GP, etc., etc. And scrolling through, it seems to have done a really good job and really quickly. And that's the power of being able to use a powerful pre-trained parsing model like SpaCy, which where all the training has been done, and we can just apply that training then um, to our new problem. I mean, it gets some things wrong. So, I mean, here we've got apostrophe S. It's picked up as an organisation, etc. But by and large, that seems like a pretty good stab at picking out named entities. And remember, it hasn't been specifically trained on this text. This is an unseen text, but it's actually managed to do this really well. So it seems that SpaCy is actually a very powerful tool that can help us to identify named entities. And I hope you've seen that it's actually a really simple to use tool as well. So one other thing we might want to do with this code is to not only find out what all the named entities are. Very often we're not interested in all named entities. We might only be interested in a named entity of a particular type. So we might just want to pick out the locations, for example, or just the people that are mentioned in a particular text. And actually, we can do that really easily because we've already got the named entities stored within SpaCy as labels in the article.ents list. So we can actually pick out whatever types of label we want really easily. So here on the screen, you'll see I've just modified my code slightly so that I've put in a for loop at the end, which basically just loops through article.ents, and then it will only print those entities, those named entities, where the label is a label person. So it'll only show me people. So really easy sort of modification we can do. So if I just show that running, where are we? Let's go over here. So I've already made this earlier. So if I now run this code, so now you can see what it's done. It's picked out the named entities, but it's only printed out the ones that it's matched to the category person. So we should only have people named entities within this list, and that can be really useful depending on our problem if we're just looking for a particular type of named entity. Or even particular types of named entities. So you might want to exclude certain things, like you're not interested in dates or times, that kind of thing, but you are interested in people, places, and organisations. That could be really useful, for example, if you're looking at survey data and you want to find out about the sort of things that are being mentioned in that survey data. So just to give an example of how that might be used. The other great thing about SpaCy is that, so we've talked about how SpaCy is utilising these big pre-trained models that seem to be really good, but they're not going to recognise everything. There will be particular words and syntactic patterns that it hasn't seen before, and which will throw it off, and it won't correctly identify a named entity, or it might identify a named entity and it classifies it incorrectly. So there are two things that we can do to improve the accuracy of the SpaCy training. So one is we can select a different model to use, and one that better suits the particular text from which we're trying to extract the information. So I already mentioned earlier there are 3 core models in English on the SpaCy website that have been trained on increasingly larger corpuses. So you can we've been using the small version. There's also a medium and large version. I've put the link up to where you can get those models and explain a little bit more about that. The core models are all trained on a range of general text, such as blogs, news, comments, that sort of thing. But there are other models available in the wild that people have developed and shared, that have been trained in more specialist areas. So, for example, if you were doing things around social media and you were trying to extract information, named entities, etc., from social media data, so like Twitter tweets or something like that, for example, or Facebook posts, people will talk very differently and using a different kind of language, particularly on things like Twitter, where they're constrained by character counts, etc. There's almost its own language. So the way in which they talk will be very different. So these kind of more general models may not be quite so good at picking those things up. So you can get models where they've been specifically trained on things like Twitter tweets. Another example is where you might have very trying to extract information from very specialist literature, like medical papers, and in which case you can get models that have been focused on that. So they'll recognise the kind of medical jargon and particular procedures and conditions, etc., that it won't necessarily have been exposed to in that more general text, but which will then help it to be able to recognise the kind of language and syntactic patterns that you would expect to see in that particular domain. So the great news is that the general models, the core models, are really good, but if you're looking at very niche areas, there are also models that you can draw on for that as well. The other thing we can do is SpaCy is fantastic in that it allows us to not just use these pre-trained models, we can also train models up ourselves, and we can add to these pre-trained models so that as well as all of the sort of general learning that it's done out there, we can also help it to identify new words and syntactic patterns that it hasn't seen before, to help those models improve, so we can add to the learning and make it gradually learn some of this more nuanced niche stuff that we may be using it for. So for example, out of the box, when I was first playing around with SpaCy, I could not get it to recognise my colleague Mike as a person. Now maybe that's something that SpaCy's onto. Maybe Mike isn't a person. Who knows? But nonetheless, it did fail to do that. And so by adding to the training, I could gradually get SpaCy to identify that Mike was indeed a person, arguably. And you can read more about how you do this, and I've put the link here. You need to scroll down to the section called Training the Named Entity Recognizer. It's actually pretty simple to do, and it will guide you through how to do that. What I will say, and they do warn about this on the website as well, you do need to have lots and lots of new examples to actually get meaningful improvement. And by lots, we mean ideally at least a few hundred. So you don't want to be adding to the training just with sort of 5 or 10 new examples. But what you can do is where you've got lots of new examples and you want to be able to add to the existing models, whether that's the core models or another more niche model that you're using, you can then really meaningfully improve the performance of the model by adding to the training yourself. So I'd encourage you to have a read through that and look to see how that works. Okay, so we've talked a lot about named entity recognition. Hopefully that's given you a bit of a flavour of the underpinnings of named entity recognition and how these kind of things work, and also reassured you that actually using something called SpaCy, you can do this stuff really easily. And as with all sort of natural language processing, and indeed all machine learning, arguably, a lot of this is about exploring and about finding out what works best for your particular problem area. But SpaCy particularly has very good built-in functions to allow you to do this effectively. So another aspect, a very important aspect of natural language processing, which we're going to talk a bit about today, is sentiment analysis. Now, we're not going to go into getting you to actually write a program that will allow you to do sentiment analysis, but I will guide you to tutorials that show you how to do this kind of stuff, not least because in order to do this, you need to install some pretty hefty software called Tensorflow is one of the pieces of software we use, which is put out by Google. Very powerful software, machine learning software, but requires very powerful computers, and also can be a bit of a pain to install. But again, we will show you links to explaining how you do this. There's also something called Google Colab, which I think we've mentioned before in the course, and which I'll touch on again at the end, which allows you to do this kind of stuff online without having to worry about installing or anything, and it gives you access to very high-powered computing to be able to do this. So we'll talk more about that later. But just for today, I just really want to talk about the process and the underpinning of sentiment analysis. So sentiment analysis basically uses AI-based methods to try and automatically identify the sentiment or tone of a piece of text, and the goal is to identify text as either positive, negative, or sometimes neutral. And in a similar way to the way in which SpaCy works, where it uses AI to predict whether a word or group of words is a named entity, here we're essentially predicting whether a piece of text is has an output of positive, which is usually denoted with a 1, negative with a -1, or neutral with a 0. So it's the same kind of machine learning neural network based approach that we're using, but this time instead of trying to predict is this a named entity, we're saying is this positive, negative, or neutral. So the overall process that we go through when we're undertaking sentiment analysis, I've popped up on the screen here, and generally you would follow this process whenever you're doing some sentiment analysis. So the first thing we do is to load in our raw text that we upon which we want to analyze sentiment. We then clean that data in some way, and we'll come back to that in a moment. We then convert those cleaned up data into numbers, and again we'll talk more about that. We then convert it into a format that's usable by a neural network. We build the neural network, then we train the neural network, and then finally, once we've done all this prep work, we then use that trained neural network to predict on our new data, to apply that sentiment analysis to our unseen data to actually use this stuff. So I'm going to talk through these steps in a bit more detail so you can understand the kind of thing that needs to happen. I'm going to skip over the kind of loading in the raw text. I mean, by this point in the course, I'm sure you're very familiar with how you load in data and raw text data and things like that. But let's move on to the second step, which is cleaning up the data. So when we undertake sentiment analysis, we need to carry out a number of steps, and cleaning up the data is a really important step within this sort of pre-processing phase. Now, we don't tend to clean up data when we're doing named entity recognition, and that's because things like the presence or absence of a capital letter, words like and the, which we tend to want to clear away when we're doing sentiment analysis, they actually might be quite important for named entity recognition because we're looking at syntactic structures. But when we're trying to look at sentiment, we're wanting to look at keywords within our text and less about the kind of syntactic structure of the text. And we're trying to use those keywords to identify, to come to a judgment call about whether we think the text is positive or negative or maybe neutral. So because of that, because we're just wanting to extract the key elements, there are a number of things that we tend to want to do before we start analysing the sentiment of the text. And these are 5 key things that you tend to want to do in this order before we go any further with sentiment analysis. So once we've read in our text data, one of the first things we tend to do is convert everything to lowercase, because, for example, when we're dealing with real world text, there will be typos all over the place, and people will write things differently. So we don't care, for example, if someone wrote the word rubbish with a capital R or with a lowercase r, or even had something like this where they've got a mixture of uppercase and lowercase and sort of typos in there. We don't care. For sentiment analysis, we just want to capture the fact that they've written the word rubbish. The sentiment will be unchanged regardless of how they've done that. And we don't want to consider these as separate words. We want to consider them all as the same word. So if we cast everything to lowercase, then we remove any of these potential issues and we can just treat it as the same word. The second thing we tend to want to do is to tokenize the text. And tokenization is just a very fancy way of saying break down the text into individual elements. So in particular, into a list of individual words. So rather than a stream of text, we break down that text, so we've got a list of all of the words that make up that text. And of course, they'll all be lowercase words if we've performed the first action. Then, what we tend to want to do is to remove punctuation and sometimes numbers as well. Punctuation in particular, rarely useful for helping us to determine what the sentiment of a text is. Numbers might be, depending on the context, but usually not. So very often we tend to just remove punctuation and numbers, and there are really easy methods in Python to allow us to do that. Then we want to what's called stem the words. Now what we mean by stemming, let's imagine we had a piece of text and the words watching, watch and watched were all in that text. Well, they all have the kind of same semantic meaning. They're different tenses, but they're all about the process of watching. It's around the verb watch, to watch. So for the purposes of this, we just want to simplify it down to the common stem and essentially just treat them all as the same word. They're talking about the verb to watch. So we can again do this really easily in Python. We can use a process called stemming, so that everything's reduced down to the common stem, and we can treat all of those separate words in the same way semantically for the purposes of trying to analyse the sentiment of the text. And then usually the last thing we want to do when we're cleaning the text is to then remove stop words. And stop words are things like a and the and etc. They're not going to help us. These kind of words are not going to help us determine sentiment. They're really useful, as you've already seen, when we trying to extract named entity, because it's all about syntactics. But actually, when we're trying to determine sentiment, they're less useful. So we can strip all those things out. So once we've got our sort of clean data, one of the first things we're then going to need to do is to convert our data, which is currently a list of words, albeit cleaned up and removed of all these sort of common words like the and stuff. We're going to need to convert them into numbers. And the reason we need to do that is because computers work ultimately at the numeric level. They work with numbers. They don't work with text. And so neural networks, when we feed things through in a neural network, we have to feed through numbers because it's going to be manipulating numeric values, as we described earlier, to try and get to a particular output. So we can easily represent our outputs of positive, negative and neutral as numbers. As we said before, we have 1 for positive, -1 for negative, and 0 being representative of neutral. But we also need to sort out our inputs. How are we going to represent our words as numbers? And there may be different ways in which we could do that, but a really common way in which we can do it, and a really useful way, is to represent words as numbers according to the inverse of their frequency within a text. And the reason we would want to do that is that allows us then to so the most frequent words have lower values. So the most frequent word in a text would have a value of 1. By doing that, that means we can easily chop out words that are used really infrequently, and from which learning will be difficult and is unlikely to give us much important information in terms of determining sentiment anyway. And we can do that by saying, well, if you're not in the top, say, 500 most common words, then we're not interested in you for the purposes of sentiment analysis. Then we can just set up a threshold of a value of 500 and easily chop out anything above that, because that means those words are not in the most common 500. So by using frequency, inverse frequency, as our way of converting words to numbers, that then allows us to very easily be able to do things like that. So the way we do that, as I say, is by looking at the word frequencies and then using the inverse frequency to determine the numbers. But as well as doing that, we also need to convert those inputs, which are now numbers, into a format that's going to be acceptable to the neural network. Now, if you're using something called Tensorflow, which, as I say, we'll send you links to at the end, this involves creating something called a tensor. I'm not going to explain what a tensor is here. If you are interested, believe me, there is a huge volume of literature out there. Most of it will blow your mind. It's kind of an abstraction of the idea of like a vector, but don't worry too much about that. Just for now, just focus on we're going to need to get it in a format that's acceptable for a neural network. And basically, what that involves is separating the data into inputs, which means the sequences of words, which remember now are represented as numbers, making up each bit of text we want to classify. So we might have a 5-word phrase that's now represented by the numbers 272, 3, 1, 6 as that sequence. So separating into inputs and also labels, so saying whether that particular sequence indicates whether that input is positive, negative, or neutral, and that's for training. So an example would be we might have a review, a review of a movie, for example, and that will be that input, that review, in terms of the keywords with all the stop words removed, etc., and converted to numbers, and only looking at the most frequent words. That sequence of numbers will be the review that we then feed in, and associated with that, we would have an output of a 1, -1, or 0 to indicate whether the review is positive, negative, or neutral. And that's we've specified that through training. So you have to have this training data where we can give it examples and say this review is positive, this review is negative, this review is neutral, etc., and have lots and lots and lots of these examples that we can use to train up our model. We also need all of our inputs to be the same size in a neural network. So we, what this means for us is we're going to need to decide on a size for our input, which is in this case is the number of words, and truncate all longer inputs. So if we say we don't want to have inputs longer than 500 words, then we'll make sure that if there is an input, a review, for example, that's more than 500 words, then we truncate, so we ignore anything beyond the 500th word. And then in anything shorter than that, we pad out with a dummy word value of 0, and that represents our dummy word. So we can choose whether to pad them out at the start or the end, doesn't matter as long as we're consistent. But that's the way of making sure that all of our inputs are the same size. And then, as you'll have seen in the forecasting training and the machine learning training, really important that we split our data. So we've got training and testing sets. So we keep some of our known data back. We don't show it to the machine. We let the machine train on the training data that we've carved out. And then once it's learned, we can then test how well it's learned by showing it some data that it hasn't seen yet, but for which we know the answers, and for which we tell it the answers, so it can test itself to say, okay, based on the way I've been training on the training set, I can now test on these reviews where you've given me the answer, and if I apply the rules in which that I've now learned, how well do my predictions match the particular data that I've got here where I know the answers. So it's a really good then gauge to make sure that, as Tom mentioned in the forecasting training, that we haven't got problems of overfitting, for example, where we've just learned the training set really, really well, but actually those rules then don't become generalizable, and that becomes useless for us, because the whole point is not to train it to be really good on the training data, it's to train it enough on the training data that it formulates generalizable rules that then work for us on new data. That's the whole reason we want to use it. So once we've got the data formatted in the correct way to be fed into the neural network, then all that's left for us to do is to then build up the neural network and then train it. We're not going to go into detail about this here because there's lots to it, but essentially what we want to do is build up the neural network. We do that by specifying one layer at a time. We gradually build that thing up. And we want to compile the neural network once that's done so that it all becomes assembled. And then once we've done that, we're then going to need to specify the training. So we'll specify things like how many epochs, which are the kind of units of learning time, the generations of learning that we want the neural network to go through. And things like the batch size, which specifies how many inputs we're going to shunt through at once, through the network at once. So those kind of things we will then specify. Then we'll start the model training itself, and then importantly, we're going to want to see get it to output metrics so we can monitor how well the neural network is learning, and also to look out for issues of overfitting, as we've just described, where it's getting too good at picking out things in the training set. But that probably then means it's going to be quite poor when as a generalized learner, when we then try to apply that learning to new unseen things. So I'm not going to go through the details of that, but I will at the end show you a link to where you can learn all about this. So what I want you to do now, we've talked a lot about sentiment analysis. Just for the next 5 or 10 minutes, I just want you to think about what you think are some of the potential applications of sentiment analysis, particularly in your areas, and what you think some of the challenges there might be around sentiment analysis. What do you think some of the problems you might encounter might be? So just spend 5 or 10 minutes on that. Feel free to share some ideas on Slack, bounce some ideas around, and then when you're ready, move on to the next video.